Hello and welcome back. So today I want to talk about thermal performance, so heat dissipation. Now normally when you have a circuit that dissipates a lot of heat, you're going to be using one of these things. So a nice big heat sink. And then you just take your high power dissipating component, so a big power transistor in this case, and you just bolt it on and everything's fixed. Now on the other hand, if your circuit has to be really small, and especially if you're using surface mounted components which don't really have a nice fixation method, like a screw hole to bolt them onto a heatsink, then you need to design your PCB in a way that it actually facilitates heat dissipation. And that's exactly what I want to look in today. So what can you do with your PCB to make it better at dissipating heat? So if you're curious, then keep watching. Today's video is sponsored by PCB Way. They provided the PCBs for today's experiment. Now, before I laid my hands on them, the PCBs look much better, so this is what they look like. These are all the PCBs, both front and back, and you can see that they're all different colors. And they're very nice colors. And the nice thing about PCB Way is that for the standard board size and part numbers, you get no extra charge, so it costs $5, regardless of any of these 6 colors that you can choose from. So the other colors do cost extra, but these base 6 colors come with no extra charge. Now, the reason why I have 6 different boards is that I want to try 6 different configurations. So let's start off by looking at the schematic, so the circuit that is on each of these boards. So the circuit on all of the boards is based around the TL-V431 voltage regulator, and the difference between this regulator and the normal TL431 is just the value of the voltage reference. So with this one it's 1.24 volts, with the other one it's 2.5. And the particular schematic that I've built is based around the high current shunt regulator, so this thing. Now my schematic looks like this. So the difference from the one in the datasheet is that I added this extra N-channel MOSFET. The idea behind this was to keep most of the power dissipation in the power transistor rather than on the bipolar transistor and the TL431. And basically what this circuit does is if we have an increasing supply voltage, it will stabilize the voltage on its terminals. So you can call this a shunt regulator or a constant voltage load. So today I'm using this with the purpose of being a load, but that has a constant voltage on it. And this is what our simulation is showing us. That once the voltage on the terminals reaches a certain point, 5 volts in this case, since the simulation is running with the TL431, with the TL-V431 it's only 2.5. Once this voltage threshold is achieved, then current starts to increase and the voltage on the terminals stays constant. So the idea behind this board is that I have 6 of these all linked in series, and the voltage drop on each of these boards is the same because of the circuit, because of the TL431, and the current running through each of these circuits is again the same because they're all linked in series. So the power dissipation is exactly the same on each of these boards. So the only difference in temperature that we can observe between them is caused by how well they are dissipating the heat. So this is the setup that I used. So I linked all the boards in series, supplied them with approximately 14.84 volts. That's roughly 2.47 volts on each of the boards. I got a current running through them of 0.6 amps, and that gives us a total of 1.48 watts dissipated on each of the boards. So almost 1.5. And if we look at the same thing from an infrared point of view, well, we can see that each of the transistors has a different temperature. So that part of the experiment went well. Now let's look at each board in particular, see exactly what happened. So the first board, the one that achieved the maximum temperature of 114 degrees, so it went really hot, was a board that on the top side had absolutely no cooling area. So we can see that on the bottom there was a copper layer but on the top side there was no extra cooling provided for the transistor. So this is just the standard footprint for the D-pack transistor. And we can see that this provided a very steep temperature gradient, so it went from very hot on the transistor to very cold right next to it. So the cooling was the most inefficient in this case. So if you don't provide any sort of cooling area, then you will not cool the transistor. Pretty obvious, really. Now, another thing that I tried was to provide a cooling area, so quite a large cooling area, but also do one of the things that is quite common out there. And that is provide thermal reliefs around the package. So this is quite useful to ensure proper soldering during reflow of your components, and in case one of the pads has a large copper area and the other one doesn't, then you will get the tombstoning effect. But from a thermal point of view, this is a very bad thing. That is because the heat will travel through the copper. So as we've seen in the very first picture, if you only rely on the substrate, so the FR4 substrate, then heat won't really dissipate that well. So by doing this, you basically cut off the path through which heat can go into the larger copper area. And that's one of the things that we almost barely can make out from this picture. So you can see that we have our transistor in the middle, and then we have this almost like a cross shape going on top and to the sides. And this is basically the effect of these little pathways. So heat is not spreading diagonally, it only spreads upwards and to the side through these cutouts. And that is one of the things that you shouldn't do if you want to cool your components. And that's exactly what I did with this board. So this is exactly the same as before, it's just that I removed the thermal cutouts. And we can see that in the thermal picture, heat is spreading out from the transistor much more uniformly. So you no longer have this cross effect in which heat only goes on a certain pathway. Heat is spreading out nicely and uniformly. So if you want to cool down your transistor, you need to ensure a copper area and you need to ensure good thermal contact to that copper area. So what can you do better? Well, there's one more trick that you can apply, and that is thermal vias. So a via you normally use to take a signal from one layer to the other. But since the vias are made from copper, so they're conductive, you can also use them to transfer heat from one layer to the other. And that's exactly what I did with this board. So here we can see that the transistor is running at around 68 degrees Celsius, whereas in the previous case it was running at 78. So I managed to reduce 10 degrees just by adding these thermal vias and taking the heat from the top layer down to the bottom layer. And normally this provides no extra cost, so you don't have to pay extra for this sort of feature. You just need to ensure that the other layer of the board has some free space where you can take the heat to. And again, since there's no thermal cutout, you can see that heat is spreading out pretty uniformly from the transistor outwards. Now, another thing that you can do to ensure better heat transfer is to ensure thicker copper layers. So what we can see here is the transistor placed on a smaller copper area, and for some reason the boards that I got have a bit thicker copper on these ones than on the other ones. Now normally if you don't get controlled impedance boards or any sort of special boards, the manufacturer will ensure a minimum copper thickness. They won't really ensure a maximum copper thickness. And well, that's a good thing. I mean, if you get more copper than you paid for, you should be happy. And what we can see here is that we have a much more uniform spread of heat from the transistor outwards into the board. So with thicker layers of copper, you will get much better heat spreading. So there's one more thing that I tried, and this gave the very best results. So from a layout point of view, it's exactly the same as the other boards, yet we get much better temperatures. So with the previous board where we had the thermal vias, we went to 68 degrees Celsius. With this one, we're down to 57 degrees, so again 10 degrees less. And also we can see that heat has spread out very uniformly. So this board has very good thermal conductivity. And I achieved this, of course, not by using an FR4 substrate, but rather an aluminum substrate. So one of the things that PCB Way offers, other than the standard FR4 type of substrate, which is fiberglass epoxy, is aluminum substrate. And this, of course, is more expensive, so the one layer aluminum board is $26, so more than the $5 that you pay for the FR4 substrate, but this has much better thermal properties. So this is quite commonly used with LED lighting and other high power products. You can put all your components on the small aluminum board and then either use it as is or take the aluminum board and bolt it on a larger heatsink. So as we can see with this board, even without using an extra heatsink, thermal properties are much better than with the FR4. And basically, this is how I got all the boards to have a different temperature. So I went from absolutely no cooling properties to a large cooling area with thermal cutouts, the same cooling area without thermal cutouts, slightly thicker copper, thermal vias, and finally the aluminum board. And you can clearly see that there's a massive difference between these. So I went from 100 and almost 12 degrees Celsius down to 54. So the difference between the aluminum board and absolutely no cooling area is more than 50 degrees Celsius. So basically, if you do want to cool your components only using the PCB itself, there's many ways, which you have to choose from, based on your design and your needs. So all in all, hope you got some useful information after this. Thank you for watching, leave your thoughts in the comments, make sure to subscribe to be up to date with all my latest videos, and see you next time. Bye bye!